Here's the example problem. We've got an electron that's in a uniform electric field of strength 2,000 newtons per coulomb that points, upwards. We want to determine the magnitude and direction of the electric force on the electron. We want to determine the magnitude and direction of the acceleration of the electron, and we want to determine what a possible source for the field could be. So let's go ahead and get started. I'm going to sketch the scenario first. We have a uniform electric field, so it's going to be evenly spaced field lines. I'll use my grid here to help out with that, and it points upwards. And we're going to put an electron in that field. E minus, there we go. There's that electron in our uniform field. So we want to determine the magnitude and direction of the force. The magnitude piece, that's pretty straightforward. Let's label this part A. The magnitude, all we need to do is take the electric force is equal to the charge of the electron multiplied by the electric field strength. This is our mg of electric forces. Instead of m, it's q. Instead of g, it's e. So, the charge of an electron is the fundamental charge, which we know is 1.60 times 10 to the minus 19 coulombs. This is a number that you can find on the AP Physics 2 equation sheet. We're just going to plug in that is the amount of charge, not the sign of the charge, because we're just looking for the magnitude in this part. And then the field strength, they said, was 2,000 newtons per coulomb. And so if I grab my calculator here real quick, I should have done this ahead of time, I guess, but I didn't. 1.6 times 10 to the negative 19 multiplied by 2,000, and I am getting 3.2 times 10 to this negative 16. I guess I probably could have done that in my head. Electric force is 3.2 times 10 to the minus 16 newtons. And we said with all electrical phenomenon that we can ignore the gravitational force because it is very small relative to the strength of the electric force. And I want to do a unit analysis over here. I had coulombs canceling with the per coulomb in my field strength. I'm left just with newtons overall, which is the unit of a force. So I am happy. Which direction will that force be? It may be tempting to say that the force is upwards because the field is upwards, but that's only true for a positive charge. Electrons go upstream in electric fields. So the electric force on an electron is downwards. So the direction here is down. All right, so there's our part A. Part B. What's the magnitude and direction of the acceleration? Well, that's going to be some of the forces in the y direction. That's got to be equal to m times a in the y direction. And I am calling, let's call down the positive y direction, because that's the direction of my net force and therefore my acceleration. So applying Newton's second law here, the sum of the forces in the y direction is just that electric force. So look at the mass of an electron multiplied by that acceleration. So solving for acceleration is the electric force divided by the mass, which we said was 3.2 times 10 to the minus 16 newtons. The mass of an electron is a number that is also on the AP Physics 2 equation sheet, or if you just Google mass of electron, it will tell you that it is 9.11 times 10 to the minus 31 kilograms. So if you're given things like a proton or an electron, they might not state the charge or mass of that particle in the problem, and it will be assumed that you will be able to look up that information somewhere. So sometimes the information needed in a problem is not stated, but you're supposed to be able to grab values for the charge of an electron or a proton or the mass of an electron or a proton from an equation sheet or from Google. So overall then, if we do that division, we end up with an acceleration of an acceleration of 3.51 times 10 to the 14 meters per second squared. There's our acceleration. Now, this is a huge acceleration, right? It was a very tiny force, but electrons have even less mass, and so the acceleration there will be very, very large. Part C, what may a source for this electric field look like? Well, let me think about that. What could generate an electric field upwards that's uniform? That means a positive test charge will be repelled from the plate that's down below. So you may have a positive plate down below, and you likely have a negative plate up above that generates that uniform field. And again, this field's only approximately uniform within there, and then it kind of bubbles out near the edges. So you have to generate it like this, and you'd have to be talking about this zone within that arrangement. And remember this, we call this a parallel plate capacitor. Technically, if these plates are infinitely large, you only need one or the other. But if you're making these in practice, if you're going to be removing electrons to make a positive plate, you might as well put them somewhere. And so if we put them on a negative plate up below, then we've effectively doubled the strength of our field without having to do any additional work, because the electrons that we remove from this plate, we just put on the other plate, and there we go. So that's our example problem with a uniform field. We'll look at electric fields due to some point charges in the next example.